Rise above oneself and grasp the world. A motto attributed to Archimedes, inviting us to pursue life's mysteries. You may already know his story about the fake gold crown. Well, long after he dunked the crown in water to find its volume, he continued to obsess over finding volumes and areas of weird shapes. Likewise, a ship he was later commissioned to build required him to invent a spiral water pump. This inspired him to further inquiry into the properties of spirals. Before we talk about Archimedes' spiral, you need to know about rope math. It's a math tool that ancients like Archimedes used. Go watch our video, Ropes and Stakes, and come right back. Archimedes' spiral is like a record. It has evenly spaced grooves. You can make the shape yourself by moving a pen in a straight line while the paper underneath it is spinning. It may sound like a complicated shape, but it actually has a very simple formula. Its radius and angle are proportional. This is because the pen and paper are moving or spinning at a steady speed. Keep this formula in mind because we'll use it again later. We're given a start line and point to initialize the spiral. Our goal is to fit a line to the spiral at a point of our choosing. So how do we do that? It seems natural to connect the 2 points and then use that line as a radius. Let's put a dot where the circle meets the start line. Then what do we do? Let's try working backwards. Is there anything here that can give us a second point on the tangent? Maybe where the start line crosses the tangent? Sometimes the start line is going to be parallel to the tangent, so that might not work. Wow, there are a lot of possibilities. It's going to take a lot of time to try them all. Luckily, Archimedes saves us the time and suggests we draw a line perpendicular to the radius. We'll use the right angle tool from the rope math video and create a dot where it crosses the tangent. If we think of these lines in terms of a triangle, the hypotenuse is the tangent, the vertical is the radius, and the horizontal is underneath the tangent, so we'll call it the subtangent. If we can calculate the length of the subtangent, we can draw a second point and finish drawing the tangent. So how do you determine the length of the subtangent? Well, we could compare it to the circle, the radius, the spiral. Again, this is a point where it would take a lot of time to test out many different options, so we'll look to Archimedes again, who points us to an unlikely candidate, the arc of the circle between the start line to the tangent point. Let's wrap the subtangent around the circle so we can compare them better. Since we don't know how long the subtangent is, we are left with 3 choices. The subtangent is greater than, less than, or equal to the arc. Let's take a closer look at these choices. We connect the center to each dot and add dots where the lines meet the spiral. Keep in mind that we placed the left and right dots at random, so they are able to move, meaning their angle can change. Of course, the middle dot cannot move. Its angle is fixed. Notice the blue angle is partnered with the blue dot. Its distance to the center is called blue r. The same goes for the red and black. Now that we have angles and radii, we can use the spiral's definition. Each radius divided by its partnered angle are all equal to each other. Since Archimedes hinted that we use the red arc, let's put these angles in terms of arcs. In order to keep our equation balanced, we need to divide by the same red radius. Now we can rewrite our equation in terms of arc lengths. In a way, the blue and black arc represent an estimate of the subtangent's length. With a little algebra, our equation can be rewritten like this. We did that because it's easier to visualize these shorter distance instead of comparing the arc and radius to the longer arcs and radii. We just look at the differences instead of the whole. If we learn more about these shorter ratios, it'll help us learn about whether the subtangent is greater than or less than the arc. Let's look at the gray ratio first. This represents the possibility that the subtangent is greater than the arc. As is, this diagram seems pretty useless, and actually that's true. Right now it is useless. We're going to use another trick from Archimedes. He knows we want to learn more about this gray ratio, so he draws parallel lines and ignores almost everything else except the gray ratio. When we draw the other diagonal, we notice that it's still not exactly the same shape as the gray ratio, but it is very similar. So we'll mark these lines in terms of being greater or smaller than the ratio. And since these are parallel lines, this similar ratio is actually part of some similar triangles. Go ahead and check yourself. You probably noticed the odd man out, which is the x. If you look at all the possible places we put our gold dot, x can range from the arc itself to 0. Look what happens if we choose x to be the arc. We get a relationship to the gray ratio. This inequality only gets more extreme as we let x get smaller, so this is the best we can do. At this point, you might see where we're going with this. But hold on a little longer, we're going to look at the other side too. This side represents the possibility that the subtangent is shorter than the arc. It's almost exactly the same trick. We mark the sides in terms of being greater than or less than the blue ratio, use the parallel lines to reveal another set of similar triangles. On this side, x can also vary, but not quite as much. After some algebra, we get this. And that gives us everything we need for our final argument. Anywhere we place our greater than and less than gold dot led us to conclude the equations on the left, but we know that they're not true since the equations on the right come from the definition of the shape itself. This means that the subtangent is not greater than and not less than the arc. That only leaves us with one option, that the subtangent is equal to the arc. This is the only point that does not lead to a contradiction. Armed with this knowledge, we can calculate the arc to calculate the length of the subtangent and then put it aside. We use our right angle tool again and place a point at the length that we calculated before. We now know 2 points on our tangent line, so all we have to do is just connect them. And we've met our goal, to construct the tangent. Pretty neat. Just so you know, we did modify Archimedes' proof so that it was a little more intuitive. There's a link in the description if you're interested to see his original proof. We suggest you finish watching the main video on tangents, or you can go straight to the next sub-video about the conics of Apollonius. If you like this video and would like to see more, feel free to subscribe and support us on Patreon.